Greetings, this is episode 17 of my engineering OddCast, and this will be an episode about the C++ project. Before we get into today's topic, I want to foreshadow something that will be coming in a couple of episodes' time. At some point, I have to make my ideas real, which means modifying a compiler or creating a static analysis tool or something like that. And the way I have always intended to do that was to modify Clang or use libclang, because I've used it in the past and I'm somewhat familiar with the internals. I was very pleased to see that an expert on the topic, my friend and former colleague Ivan Marashko, has written a book on the internals of LLVM18 as far as the front end goes. He's not paid me for this review. He's only aware that I'm saying anything at all because I had to ask him to do a voice note of pronouncing his name because I didn't want to get that too wrong. I'm sure I have got it wrong and I apologise for that. As I say, do go and get this book if you're at all interested in doing this kind of thing yourself, or even just if you want to follow along with what I'm doing. It will help you. Now, I have it on Kindle, I don't have it physically, so you're going to see the cover now using whatever special effects I can do, which I'm not an expert at, so who knows how good this will look. Now on to what the topics in this episode are going to be. I promised I would show you what the various well-known techniques for doing custom data types look like in debuggers and what the consequences of that are. I will be showing you that. I said I would try to recreate a problem that I'd seen with the mixin class technique that is related to how C++ defines overload sets and try and explain that. I have done that. As I think I suggested before, it is a pretty niche problem, but it is worth being aware of before you set down the road of using mixin classes, that you are potentially storing up this problem for yourself later. It's not difficult to resolve. It's not something that's going to occur as a frequent occurrence should you pick mixin classes, but it is a pain in the neck to try and work out what's going on if you don't already know the answer. So I would suggest watching, because I can show you what the outcome is and how to resolve it. And then the last part of the video for this week, I'm going to show you what is very unsatisfying for me, which is my partial, incomplete thoughts on what we could do that might have the potential to be better with a lot more development work. It's uncomfortable for me to share this stuff because this is the part of developing an idea that I would not be showing other people usually. This is what happens that I then go, no, that's not good enough, or it needs a lot more work before I waste anyone's time with it. The reason I want to share it with you is that it is a real part of a project life cycle, and I think if you're a junior engineer, perhaps you don't get to see this stuff and you think that senior engineers come up with coherent, fully formed ideas like that. It could be that that's how other people work, but it doesn't work, isn't how I work. I have a succession of frankly bad ideas and I try to refine them, knock off the bad corners, and so you end up with hopefully a good idea left at the end of it. Or sometimes you end up with what seemed like a bad idea, but having examined everything else that's possible, it's less bad than doing nothing, and it's less bad than anything else you thought of. And so at this point, as I'm showing you these thoughts in this episode, none of them are things I would ever normally show someone else unless we were working together on this conceptualizing stage of the project. So I've made a simple program that just crashes with a divide by zero error. And my intent here is to see what a automatic triaging system or a first level support engineer might see in order to assign the crash to whoever's responsibility it is, using straight aliases. Here we have the line with the integer divide on it as the line with the crash, and when we look at our stack backtrace, it's in the file that has that line in it. Like, nothing here says immediately to the triaging engineer that the problem is that this is zero, but they're going to send this bug to the owner of this function, which is a reasonable first place for it to go. It's someone who has some context about what's trying to happen here, because it's the person who wrote the divide total quantity by quantity. That person who it's assigned to would know quantity must never be 0, so the bug is further up in my code, or someone has promised something isn't 0 when it is, and that's what's going to get debugged and fixed. This is not a perfect debugging or triaging experience by any means, but it's fairly acceptable. Let's look at what happens with enum classes, and to save our eyes a bit, I'll reset the terminal. Here we see the immediate peril of wrapping stuff in the top line in the backtrace is now from a header file, and the person who wrote this operator library part of the system of types isn't responsible for checking the parameters make sense. The caller is, so this bug should go to the owner of this, but it is likely to get automatically triaged to the owner of this function. It's not a disaster by any means, because at least the owner of this is going to immediately be able to look at this part of the debugger output and say, well, your left parameter is fine and actually it's irrelevant, that could be 0 anyway, but your right parameter is 0. So you've asked me to divide by 0, which is impossible, and they can immediately reassign it to the owner of this without having to think about their code at all. And indeed, anyone stumbling across this bug in the process of development, let's talk about that use case as well, they're going to be able to see, because of the way this debugger works, that the right side is 0, and pretty much every programmer knows that a divide with the right side being 0 is going to be a bug. So again, they're going to, in the process of debugging during development, just pretend this line doesn't exist and start debugging this function, which is the right thing for them to do. Let's look at what happens with my normal classes, which I mean, hand-rolled operators. Again, we have the top frame is inside a type library function. Obviously, it's going to be. This time we don't have any, nothing built into the debugger is aware of how to unpack these object types to show that the right side is 0, so we don't have that information anymore. So this is going to go in automatic triage to the owner of this function. Obviously, you could train people not to do that, but the way I think about this actually is what the response of a junior, mid-level and senior engineer would be on encountering this backtrace in the course of development would be. A junior engineer might not have seen this kind of pattern and would then dig up this function or try and contact whoever wrote it to ask them, why is your code crashing? And they'd have to have it explained to them that, this will crash if you pass in a 0 valued thing here, which must be what's happened. But it is to some extent a waste of that junior engineer's time and of the more senior engineer who has to explain it to them's time. Mid-level engineer will have seen this pattern hundreds of times before and will probably just completely disregard it and immediately jump to debugging this piece of code, which is, generally speaking, a reasonable thing to do. A senior engineer probably will be paranoid enough not to do that and will actually go and look at what's the implementation of this, is it really doing the right operator that it claims? Because it's really easy typo to end up with the wrong thing here. And they'll spend time checking that. They might think about putting any protections they can do inside of this function to stop this from being a signal in this case. Would it be better if it was an exception? Blah, blah, blah. So all of that work will happen, and then they'll get on to debugging this once they've satisfied themselves that this is doing what it appears to claim it does. All in all, that one will cause a lot more work to have to happen than either of the first two we looked at. Now let's look at if we're using the funky template mixin classes. Again, obviously the top frame is in a function called operator /. Again, it's going to, if it's naively triaged, it's going to go to whoever implemented this template. If it's slightly less naively triaged, it might go to whoever implemented the class that extended this template in this case. But interesting that the debugger doesn't want to surface that here. Could have surfaced that the actual type of self is a quantity. I want to be clear, I'm not intending to critique the choices that debugger implementers make. They have to make choices about what they're going to surface. Because of this being a template parameter, we have the this type spelled out for us here. If a junior engineer who is not aware of all these patterns sees this, it's going to involve them using some of the time of whoever it is who owns these mixin classes and whoever wrote this function to understand why that's crashing. And it will eventually get through to, look, it's just you've called it with a 0 on the right-hand side, and that's why it's crashed. A senior engineer who's aware of the realities of C++ but's never seen this pattern will definitely go and investigate what the hell is going on here. And very senior engineer who's paranoid will, of course, go and investigate this code anyway. So again, this pattern will involve a lot more engineers' time getting used whenever anything goes wrong than straightforward aliases. It's not wasted time in that it's very possible for this function to have been written wrong, and that could be the cause of a crash. Possible this class is structured incorrectly, and that's the cause of a crash. And because it exists, that has to be investigated by anyone doing their due diligence. Once you satisfy yourself that that's safe, or if you take the pragmatic approach of assuming that's safe and debugging everything else first, and you go and find the real problem in here, then cool. But my point is to say that when we look at the assembled code of all of these programs, they're going to look identical in a release build because everything's going to get inlined and it's just going to do some int divided by another int. It'll be literally the same machine instruction in all 4 cases, and it will be a single machine instruction, and that will raise a trap which the kernel will convert to a signal, and then the program will crash. Fine. The only difference in here is what the debug experience is like, and it does matter that the debug experience costs are different. I also think it's worth saying that the debug costs will differ depending on what debugger you're using. So I have exactly the same programs to run with the same, just run it, wait till it crashes, show me the backtrace, and then quit with LLDB, and let's see how that goes. Straightforward aliases, as we're expecting, we see the top frame is in the div0 function as it was with GDB. With the enum classes, of course, the top frame is now inside our operator / function. This is quite interesting. Do not interpret what I'm saying as criticism of either debugger, but the fusion of the two here would give you almost perfect information. So LLDB has found out the additional detail that it's an integer divide by 0, which GDB never told us. It just told us it was sigfpe. Okay, cool. LLDB therefore is the better debugger for this scenario. But hold on. In GDB, we saw left equals 200, which I'm pretty sure is the same as C8, and right equals 0. We didn't know from what GDB told us that the problem was a divide by 0, but we did know that the right operand was 0. Whereas in LLDB, we know that the problem is divide by 0, but we aren't told what the right operand is. So we've won something, we've lost something. It's interesting. Fundamentally, we have almost the same information here. I mean, we have additional details about stack frames that GDB is programmed to ignore. That's cool. I actually like LLDB's decision to give us the library that the function it's telling us about was linked into, because that can be a interesting source of bugs in other situations. In this case, it doesn't make any difference. But again, my point is the same from whichever framework you're using to get your stack backtraces. This one tells you to go ask the implementer of this function, whereas the aliases were telling you to go to a place that's closer to where the problem is. I won't talk through them, but here are the normal class and mixin classes. Again, nothing particularly stands out useful here. So, I mean, we've got the address of the objects, but we haven't told LLDB how to print these things. I think that's illustrated what I wanted to say about the debug time cost of making different decisions. And I will say that overall what I'm looking for, if I can find it, is a mechanism to have the debugger point at the line where you have asked for the divide by 0, and for that to be what everyone agrees is a safe thing to do. Which means one of two things to me. It means either these functions or whatever mechanism it is that makes the divide operator exist on custom types is generated by the compiler. So there's no engineer written code, and therefore that code can't be wrong. Or that code is written by humans, but verified by the compiler to produce exactly the result that it's asserted to produce. Again, so that everyone can be confident we do not need to audit these functions at the point we're debugging a program that uses them. I think that's going to be extremely difficult to do in either case, but if we're talking about what do I think would be an ideal outcome of a process here, that's part of it. It is a thing I want to aim for. I said in the last episode that there was a potential issue if you used mixins relating to the concept of overload sets. and I would try and reproduce that to see if it was still an issue in C++ 23 and to show you what it looks like. It is a pretty niche thing, even by the standards of this podcast. I'll just show you the types and definitions on a non-mixin. We have this structure named no compound addition source. We have this structure named yes compound addition source, which is implicitly convertible to a no compound addition source. Just how it is. I'm not saying that this class structure makes any great deal of sense. This is the least amount of code I could come up with to show you the problem. So it is for you to judge if you think this class of problem could exist in your code base, or if your existing coding rules make this kind of thing impossible. I'm not trying to say that what I've done here is a reasonable thing to do. I'm trying to say this isn't just to illustrate the nature of the problem. And then we have a class called compound addition target. What we have is operator plus equals between compound addition target and no compound addition source isn't allowed. So that I've explicitly deleted that operator plus equals. And then we have a plus equals for compound addition target and yes compound addition source that does exist, and its result is a compound addition target ref. Basically, if you've got one of these and you plus equals one of these, it should work. If you've got one of these and you plus equals one of these, it should not work. With straightforward type aliases, I can't make that happen because they're all unsigned, and I can't make this unsigned add to this while making this unsigned not add to this. With enum classes, there's two different types. I can make it not work in the way I would expect. With normal classes, there's two different types. I can make it not work in the way I'd expect. Mixin classes, what I've decided I want is if you add these two with just straight operator plus, that's permitted and you get a new one of these. But you're not allowed to plus equals these two. I don't want to make up a story of why, but as I say, I have seen this in the real world. I'm not going to share someone else's secrets. So with our mixins, what we've got in our add mixin is if the return type and the type of the this pointer are the same, then plus equals is always there. And plus is always there, and plus equals is also there if these types match. What we've got here is this mixin is going to add plus and plus equals for no compound addition source, and this mixin is going to add plus and plus equals for yes compound addition source. Because we're in a subclass here, we can specifically override. So this is going to shadow the operator plus equals that we pulled in from here. This is going to shadow that one and be explicitly deleted. So if you try to do plus equals with one of those, it's not going to work because it's explicitly deleted. The problem is adding this also effectively kills off the plus equals from this mixin. And the reason that happens is when you write a plus equals B, let's say A is one of these compound addition targets, okay? So A is one of these. Plus equals is going to get translated to a call to operator plus equals, in this case, because that's a class. Let's say B is a yes compound addition source. The compiler looks on A for anything operator plus equals. And when I say on A, I mean literally in the class. And for free functions that have exactly the right class name as the first operator. So in this case, that first scan is going to find exactly this function and only this function. And it then asks, is B one of those? The answer is no. The next loop is B implicitly convertible to one of these? And the answer is yes. Yes, it is. And the compiler says, that requires one implicit conversion. There was no plus equals that required 0 implicit conversions. This one required one implicit conversion and was available in the first overload set that I looked at. We can't find a better one than that. Therefore, this is the one that happens. Therefore, this line with a yes compound addition source as B will not compile because that operator's been deleted. And that might not be what you expect. The way to fix it is to add this line of code. So this says the function, member function operator plus equals from this parent class. Pull that into this class directly. It's no longer available on this class merely because a superclass implements it. It's now available directly on this class. That's what the meaning of this using is. If you were to add that, then when the compiler does that first scan, it finds this operator plus equals, and it finds this operator plus equals, okay? And then it does the same rules as before. Can I call this one with no conversion of the type conversion of the right-hand side? No, I can't. Can I call this one with no type conversion of the right-hand side? Yes, I can. Therefore, this is the unequivocal winner. There are 0 conversions required, and that's what I'm going to call. It's just something to be aware of. There's other ways I could have designed around this problem. I could have made a mixin that is add only, so doesn't allow plus equals, the compound add equals operator, and I could have used that here. I wouldn't have needed to delete it because it would not have been defined, and then I wouldn't have had the compiler finding this first, and everything else would have been cool. My point is that this is an important difference actually between what the behavior of normal classes and mixin classes is. It does matter that these functions exist only on superclasses and not actually in the class itself. And if you want to make them truly identical, then you have to write one of these usings for every single function you've mixed in, and that makes it not mixins anymore, in my opinion. As always, you do you. I'm just trying to show you some of the things I've thought about and the problems I've run into. Let's talk about how I've approached starting to design possible future syntaxes and semantics for things. Basically, I've sat down and typed in some things that felt like they made sense to me in order to see if they really do let me express everything I want to express, how communicative it is, and whether it, in a theoretical sense, works for what I'm trying to do. So my first idea was to take the restrict keyword, which is not meaningful at the moment in C++. It is meaningful to C, and I'll come back to this in a few minutes. But to take that and insert it into using. So I said, let's say that we can forward declare a thing here. So using quantity is a restriction on unsigned. And what that's going to mean is that the underlying storage for quantity is exactly an unsigned, and all of the possibilities of what you can do with a quantity come from what you can possibly do with unsigned as a fundamental type. But we're not making it a straight alias, we're applying restrictions to which of those operators we're going to actually allow. Then we have the complete declaration. So I've again written using quantity equals restrict unsigned, and now there's a scope block, and inside of the scope block is a list of what you can do. Anything not mentioned in here you can't do. So actually, let's look at customer ID. I've said customer ID has a default constructor. Customer ID can be explicitly converted from an unsigned and can be explicitly converted to an unsigned, but you can't do anything else to that. In the real world, I would want quantity to have these operators as well, but I decided for the purposes of exposition to say quantity can only be got by using this literal suffix. So you would have to write to get a quantity, and then it allows the increment decrement operators, both pre and post fix. Inside of this scope, you say what it is, and the only thing you're allowed to put on the right hand side is equals default. You can't write custom versions of any of these operators. You said this type is a restriction of this type, and you're only going to expose these operators, and you can't in this syntax change what the return type of these is. It's always a quantity or quantity ref in this case. This is how I was exploring this idea for syntax and semantics. All of these are first passes, all of the ones I'm going to show you, in fact. But I thought the rules for this file are broadly that the initialization and conversion rules have to be inside this scope. But let's try allowing the other operators and so forth to be defined as existing with the same equals default syntax outside of those scopes. So you can say outside of the scope of either line price or quantity that both directions of that operator style work, and so on. I think that having these separately probably causes some problems. So I wanted to look at what if I say, well, it's got to be everything you want to say about that restricted type has to be inside the curly braces. So here's exactly the same type set as I had before, but entirely defined within the curly braces. Now we have on some of these functions inside here, we have a changeable return type. So multiplying quantity by price could return any type that is compatible with it. So here we want line price. And that makes it inconsistent with these other types like decrement, increment, the suffix. It's not possible for you to change what these have as a result type. They have to be quantity or quantity ref. The syntax gets inconsistent in that these guys now don't have a return type attached to them and this one does. I think that causes massive parsing consistency problems. So this syntax, as it's written here, probably doesn't work. You would have to add return types to these for here. I think the rest of the file does have return types everywhere it needs them. Again, it's an experiment to see, firstly, whether I like it enough to want to pursue it, and secondly, whether I think it's reasonable enough to try and argue to anyone else that this is a good idea. And so far, the answer is not really, or at least I think I can do a lot better, so I'll just carry on thinking. So I've written our default constructor, allow it to be static cast from the underlying type and to the underlying type explicitly in all of the scenarios. So how about we make that behavior the standard behavior, which seemed reasonable as a first thought. But then sometimes we want to be able to say, actually, no, you can't do those things on this type. So that means as well as equals default, we're going to have some equals delete. A couple of our types reduced to there's nothing extra going on in here. And then the quantity which we've been restricting, we now delete explicitly those parts that we have by default that we don't want. And here we are redefining something that we would have by default because we want to change the explicit nature to an implicit conversion. This is basically the same as idea number one, but with these things implicitly defined and less explicitly deleted. And I kind of like that more because it's a bit terser, it's a little bit more obvious. And then here is the same thing as idea two, but with the same rule change. So we're only allowed to define these defaulted things in line with the restricted type, but we still have the implicit zero constructor and then static cast to and from the underlying type. Well, we're still looking at this one, which is the last one of that family. Let's talk about how hard this would be to standardize if we wanted to push forward with it. This keyword is currently not permitted in this position. So that's good news because it means that this line as it is now doesn't mean anything. If it turned out to be a problem, we can pick another keyword reserved for standardization to mean this same concept. So it's not the biggest problem in the world if we needed to find a way around that. The thing that puts me off this is that this block of a whole new meaning of what's inside it has to exist at the same time as introducing restricted type def kind of concept, because otherwise the C++ compiler doesn't know what to do when you try and do any of these operators. I think that I don't necessarily want to try and do that because it's such a big load of stuff at the same time. Can I make this part sufficiently meaningful on its own that I don't need these for the compiler to do a complete and coherent job with the source file? Because if I can come up with a way for that to be meaningful, what that allows is the content of this, or the definitions of what should be allowed, we can push that into an attribute rather than making it part of the language. And the advantage of an attribute is that they don't need to be in the standard. If we can get to a world where the compiler does the right thing, produces the correct program if it understands this but doesn't understand any of this, then we can move this part here into a static analysis tool that we run alongside our compiler to check that these rules are being followed. We can iteratively refine that. We can work out the syntax of that at our leisure. And once we have something really perfect, we can persuade all the compiler implementers to implement the same syntax with the same attribute name, and whether it at that point gets adopted into the C++ standard or not is actually irrelevant. Once all the compilers support it the same, it's good enough. One of the things that made me think it's probably viable is the rules on what can be in an attribute are such that as long as you make sure all the brackets and quotes of various kinds are in matched pairs, which they inherently are with this syntax, there's not a problem with allowing compilers to ignore it. We move on to a first pass at a way of making this meaningful without having to specify what's allowed here. My first attempt was to define it such that if you've got using x equals restrict y, it means x is y, x ref is y ref, x star is y star. So these are like, it's not even a conversion in terms of the compiler's cost model of which thing it prefers to bind to. If there's a function that takes yref and it's got an xref, it is the cheapest change to make an xref into a yref. It's at the same kind of tier as integer promotion from an int to a long, which is considered to be cheaper than a normal implicit conversion. That's what I was trying to define here. So they are distinct enough so that you can overload a function to have one with parameter xref, one with parameter yref, and they will be called with a type of xref will go to the one that said it wants an xref in preference to the yref. So they're not the same in the way that a straightforward using is, but they're only one step less the same than that in terms of converting from the alias type to the underlying type. Opposite is not true. You can't convert implicitly at all the underlying type to the alias type. You have to do that with static cast. And all those static casts for going the opposite way to these things are 0 runtime cost, but you do have to type in static cast to do them. So in a sense, this seemed similar to public inheritance to me, in that if I had x extending y, it is true that all of these conversions are true, and this is not true. In fact, those aren't true. You can't static cast a underlying type to a derived type safely. We are guaranteeing that it's safe as well as 0 runtime cost in this model, because it is the same, but it's just a new name for the same thing. The other differences from public inheritance are y here could be final, it could be a basic type. Neither of those two work if you're trying to use public inheritance. X has exactly the same member storage and member functions as the alias type. So it's the same size, it has no additional storage, it has no additional functionality. It is the same, just a different name for the same thing, which is why all these 0 runtime cost static casts are safe and free. Now for this first pass, I introduced this rule, which we'll see later why it turns out to be a dumb idea. But my idea with this, you've got things like std hash, and std is integral. If I say using x equals restrict int, I don't want to have to override all of those trait types to make it x look the same as int, because it is the same as int. So that's why this rule I introduced. So the rest of this file below this line is me trying to think through some basic consequences of this set of rules that I've come up with. Follow the link in the description to the tag on the repo to see for yourself all the parts I thought were good. But the problem areas I found for myself pretty quickly were, if I've said using B is restrict A, and this is the definition of A. So A has a this auto type parameter. So here, inside this function, when the compiler is evaluating this function, what is the type of self? Is it always A, or is it B when B is a restriction of A? In particular, this matters for this function because it's going to return decal type auto. So this will be a reference to a B or a reference to an A, depending on what we choose. Now this function inside of A is declared as returning an A, but it's got a self template parameter. Is self in this function going to be an A or a B? I think it's got to be the same answer as here. Are we expecting the compiler to rewrite the return value from A to B because of the aliasing, because it's been invoked via an alias, or return an A always? If you've got things like operator plus plus on the class, what does it mean when returning a reference of its own type? We have a legitimate choice to make here about whether this auto expands to A or B, because the nature of anything using this auto is it must be an inline function. So we'll be expanding it at a point when we know whether the underlying type name is A or B. So that's fine. It feels a bit too weird that these kind of functions, which could be out of line and therefore in a separate translation unit and have no concept of the type B even existing, this therefore would always return a reference to an A. And are we expecting the compiler to know that that result should be rewritten to bref in this case? Like, how can the compiler know to do that? If it can see this implementation, then sure, we could try and argue that the compiler should be smart enough to know that it's returning star this inside a function that was invoked on an instance of a B, therefore star this should get rewritten to bref. Okay, fine. But what if this is some kind of linked list iteration mechanism, and the references it's returning is to the next thing in the chain, are we then sure that we want that to be treated as a B and not an A? I couldn't convince myself that I could make all of these parts super consistent before I thought through all of that stuff. I thought, okay, well, what would the attribute syntax look like, or could it look like? So I defined, this is the same as number 5, except without the thinking about what can go wrong, and with the addition of, here are the things I want to permit. Some of the issues you run into with number 5, you can solve if you had the information from number 6, because what the compiler should deduce all those autos to is defined in these attributes. But that defeats the point of making them attributes, because it's no longer optional, it's no longer something that a correct compiler could just ignore. I don't think these are the answer as described here, but I did think, well, hold on, what about a different meaning for using x equals restrict y, where we allow it to be static cast in either direction, and obviously there's still static cast equivalents for const, volatile, reference and pointer combinations over the x and y. And then you use something like the deduction guide syntax introduced with C++17 to say what other things are allowed. Rather than equals default, this is basically replacing the equals defaults with a deduction guide so that the compiler can know what the result types of things it should be deducing are. I took the same set of thought experiments from idea number 5 and tried to apply them here. It solves a few more of the problems that I found, but I think there are still plenty of new problems, not least that we have to introduce a new keyword because we now need deduction guides on functions other than constructors, which is a massive change. So I don't think I believe in this as the answer either. This is a really unsatisfying video for me to make, but I promise to show you the real process. And it's unsatisfying because nothing I've shown you here is in the zone of, I think actually this is a good idea or a reasonable thing to do. They're not obviously dumb ideas, because if they were, I just wouldn't have investigated them at all, but they are in the category of ideas that once examined turn out to be poor, and you have to pass through this toll booth area, as it were, on the way hopefully to getting reasonable answer for what to do. Let me give you an idea of what I'm currently thinking about, which isn't written down anywhere. During thinking about I think it was number 5 was where I first did this, I wrote down how it differs from public inheritance. And that started me thinking about, what am I trying to do here in more abstract terms? What I'm trying to do is have the same underlying storage and behavior with 2 different type names, and for that to be in a coherent place. And there are 4 obvious existing such dualities in the C++ standard. So we have private inheritance, we have protected inheritance, we have public inheritance, and we have straightforward type alias of using. And to rephrase what the whole point of this is, I'm not personally happy with using any of those 4 mechanisms for this purpose. I think they end up overly verbose or can't be made to do the job I want to do, and thus I'm looking for another stable point. It occurred to me to think, well, the reason I'm having trouble making any of these consistent with the rest of C++ as it exists today, a lot of the problems I have are to do with what's the result type of an operation. How am I going to explain what the result type of an operation is? What it occurred to me to think about was there's a few other dualities that are not straightforward using. They're not straightforward public inheritance or private inheritance or protected inheritance. And those are, for example, so I'm going to use type names from Windows. I have a type called int, which is 32 bits, and I have a type called long, which is 32 bits, and they are interconvertible, but I can make a function that takes an int and a function that takes a long, one overload the other, to have different behaviors, and that just works. On my Linux platform, the same duality exists, but the pair of types would be long and long, long, and they're both 64 bits long. Same point stands, though. I can write a function overload set that includes a long and a long, long function, and even though the underlying storage and what you can do with them is exactly the same between those 2 types, that overload set is valid, and the different overloads will get called differently. Is that, in fact, what I'm trying to do here? And I think the answer might be yes, but it also might be no. So I think it's significantly different from the long and long case, because I explicitly don't want everything into convertible implicitly. Yeah, I don't want to have to establish a straightforward promotion hierarchy amongst types. That is another stable duality in the standard, but it's not what I'm looking for. What about the duality between like char16t and uint16t? Those are not the same type as each other, but they are like the same size and they're both some kind of integer, but you aren't allowed to freely interconvert with them or use the same maths on both of them. So is that what I'm looking for? And the answer is, again, maybe. But the way I'm starting to think about it now is that perhaps I should be looking for, as well as a solution to the problem that I think I have that I was originally trying to solve, it would be cool, or it might be a useful set of test cases to ask, whatever I come up with, can I use it to describe those dualities as well as the dualities I have in mind? Because if the answer's yes, then we can perhaps rewrite some parts of the C++ standard to be char16t has this definition exactly as a restricted using of int16t or uint16t or whatever, rather than having to say here are its properties and what you can do with it in standardese. We could write it in C++. And the advantage of that would seem to be that the next time someone comes along and asks for a new basic type, you can turn around and say, well, look, you can make your own new basic type with the same tools we've got in your own namespace. Why are you even bothering us? Which I think might be a nicer place for the standard to be. If such type turns out to be generally massively useful, then there's no problem incorporating it into the standard in a later version, but you could wait for the evidence for that to happen first, and for the type restriction definitions to get debugged in the wild before importing it into the standard, rather than having to make it standard first, which is, I think, the current situation. Anyway, that's my current line of thinking on this stuff. As with any other thing, it may go nowhere, it may turn out to be good, who knows. The other thing I'll say is I do think that having it be some other keyword around type alias of using does seem to me an intuitive way to do it. However, if I'm going to do that, then I have to make it work for C as well as for C++, because I do not wish to introduce a difference in what using and what type def can do. Also, I think that C has the same fundamental type addition problem that I was just talking about, and it would be nice if I can solve it for the C standard as well as C++, which means I need to go and read the C standard because I haven't kept up with what's happened since C99. So yeah, that's homework for me to do. Thank you for watching and listening. If you've made it this far, I imagine this is going to be pretty long once I've edited it. Thank you so much for your time and attention. Reminder to, if you don't already have the knowledge that it contains and you want to play along as in the future episodes, go check out Ivan's book. I'll link it in the description below. Have a good week, and I'll see you in the next episode. Cheerio.